So we're back with part 2 of particle physics. So obviously part 1 was the stuff that, well, I knew. This is the stuff that I am learning here. So revision cards, very simple. So the first part is classification of particles. So this is going to be like one revision card, one explained, etc. So classification of particles. So all particles are either hadrons or leptons. So basically that means that their differentiating property, the thing that makes them seem different, are that leptons are fundamental. Leptons are fundamental properties, which means that they are the smallest thing possible and cannot be broken down any further. So basically this kind of tells you that hadrons are not that, they are not the smallest thing ever, so they can be broken down further. So as far as leptons go, because they can't be broken down any further, they also do not experience strong nuclear force. Yeah, so the opposite would be hadrons, which are made of quarks. Which are also fundamental properties, so they would experience a strong nuclear force. So what we've learned is fundamental forces do not experience a strong nuclear force. So basically, just to summarize, hadrons are made out of quarks, so that means that they are not the smallest thing possible, while leptons are the smallest possible thing. So hadrons can be separated into byrons, antibyrons, and mesons. So byrons are formed of 3 quarks, and antibyrons are formed of 3 antiquarks. While mesons are formed of a quark-antiquark pair. So just to summarize that part, so all particles are made out of hadrons and leptons. Hadrons are basically the things which can be broken down further into mesons, byrons, and antibyrons. Byrons have 3 quarks, antibyrons have 3 antiquarks, and mesons have a antiquark-quark pairing. Leptons are a fundamental property, that means that they cannot be broken down any further. So Lepton number, I don't know how to pronounce the word. So the Lepton number of a particle would show whether it is a baron or an antibaron or not a baron. So Lepton number 1 means baron, 2 means antibaron, and 0 means not a baron. So this is always conserved. So another thing, the only stable baron is the proton. This means, as we know from radiation, that every other type of baron would eventually want to become a proton, because obviously they want to not be unstable, they want to be stable, and because they want to be stable, they would become the most stable thing possible, which in this case is a proton. So now Lepton number So obviously 1 means lepton, -1 means anti-lepton, and 0 means not a lepton. I don't know why they've included that, for sure. So there are two types of lepton numbers, electron lepton and muon lepton. Lepton number is always conserved. So two types of lepton numbers, electron and muon. So that kind of looks like mone. So a muon is a heavy electron, so it decays into a electron over time. Simple. So baryon number 1, 2, 0. Lepton numbers 1, -1, 0. Baryon, the most stable one, is a proton. Everything wants to become a proton. Lepton, you can either get a muon number or electron number. Electron is the most stable, whereas muons are heavy electrons, so they eventually become electrons. Simple. So now strange particles. So strange particles, these are produced by the strong nuclear interactions but decay by weak interactions. The only strange particles that you actually need to know about are kaons, which decay into pions through weak interactions. Strange particles. So the thing I'd write here is strange particles made by strong, broken by weak. All you need to know. So that is all you need to know is kaons become pions. Simple. Strange particles, they are made by strong, broken by weak, and kaons become pions. Simple. So strangeness. So this is a property, so kind of like charge, mass, etc. And it shows that strange particles must be created in pairs. As strangeness must be conserved in strong interactions, however in weak interactions, strangeness can change. Strangeness, another property, must be conserved in strong interactions, but in weak can change to +1, -1, and 0. Lovely. So, quarks and anti-quarks, these are very simple. So, are they? Okay then, we'll think about it. So, quarks, they are like the smallest thing possible. Protons are made out of quarks. Baryons are made out of quarks, so they are tiny. And quarks, there are, I think there's 6 or 7. There are 3 you need to actually know. And these are the up, down, and strange. Up, down, and strange quark. So the up quark, this has a charge of +2/3, has a baryon number of +1/3, and 0 strangeness. Sure, let's just leave it as that. So I'm going to scum back this a bit, and that. So up, down, and strange. I don't think you really need to know like the basics of it, but it is good to know about their properties. So down quarks have a charge of -1/3, and strange quarks have a charge of -1/3 as well. they all have a baryon number of a third, but here the strangeness is -1 because it's a strange quark. So quarks are combined to form baryons and mesons. For example, quarks combined UUD, so an up-up-down quark, would form a proton. This would be because a proton would have the baryon number of 1, as you can see here. UUD would be a third plus a third plus a third, which would be 1. And protons have a charge of 1. Thus, 2/3 plus 2/3 minus a third. Thus 1. Simple. So, you need to know conservation laws. So, conservation laws. So the things that are conserved are energy and momentum, and charge, baryon number, lepton number, and muon lepton number. So these you have to know conserved. So conservation laws, these are all conserved during anything really. And like to make sure this is conserved, like obviously the neutrino was made to make sure energy and mass is conserved. Speaking of which, mass should be there, but it's not, because they're not really that necessity. So strangeness must only be conserved during strong interaction, so I don't think that's needed here. So okay then, how you would actually do this. So say like you were doing, like can I show this? I think I can actually. So theoretically, let's just say no, I can't show this because then I actually have to but say you had something which was a neutron would be a proton plus an electron plus a neutrino. Yes? So these would have things such as charge, baryon, electrical lepton number, muon, and strangeness at the start. So you would have certain values. So what you'd have to do is you would have to show, using formula and maths, that after the interaction, all of the values are the same. So that's all you need to do basically to be able to prove these laws. So that is the end of particle physics.